Hello friends, myself is Dr. Bhavin Patel. I am lecturer in chemistry at Natubhai V. Patel College of Pure and Applied Sciences, Vallabh Vidyanagar, Sardar Patel University. Today we are going to describe certain topics related with chemical kinetics, and these topics are the mechanism and rate laws, relation between experimental rate law and rate constant which is derived from mechanism, the equilibrium constant of reaction and rate constant for each elementary steps and their reverse reaction, then collision theory of gaseous reaction and temperature effect. Friends, we know that for any complex reaction, as it consists of a set of one or more elementary steps, it will having certain mechanism, and for one reaction, for one complex reaction, there may be more than one mechanism, but at instant that reaction will proceed only one mechanism. Now the question is, how one can propose the mechanism for any given complex reaction, and for that we have to keep certain points in mind, like the experimental rate law and the stoichiometry of reaction. The second point is the experimental condition under which it occurs, means that reaction proceeds. And third most important thing is information from other possible sources like spectroscopy and all these things. So first we'll try to understand how temperature, or in general the experimental condition of reaction, affect the mechanism of reaction, and for that we'll take one suitable example for this. The example is reaction between NO2 and CO. It is known that when this reaction proceeds at above 500 Kelvin temperature to produce NO plus CO2, then experiment suggests that the experimental rate law R depends on the concentration of both the reactants, that is NO2 as well as CO. It means that above 500 Kelvin, the rate of this particular reaction depends on the concentration of NO2 as well as CO. It is first order with respect to NO2 and first order with respect to CO. Overall, this reaction is second order. But if same reaction is proceed under certain condition of temperature, means other than this condition, that is say below 500 Kelvin temperature, then experimental result suggests that the rate of the same reaction depends on concentration of one reactant, that is NO2 only, and it is independent of carbon monoxide concentration. So the reaction is same, but if we change the condition of temperature, the same reaction is proceed above 500 Kelvin, it suggests that rate of reaction depends on both the concentration of reactant. But if the same reaction is proceed below 500 Kelvin, then the rate of reaction depends on concentration of one reactant only. So we can say that above 500 Kelvin, this reaction is elementary reaction, that is the single step reaction in which there is transfer of oxygen atom from one molecule to the another molecule. But if the same reaction is proceed below 500 Kelvin, it is no more elementary reaction, but it is complex reaction, because it will proceed in more than one step, and therefore the suggested mechanism for the same reaction below 500 Kelvin can be written as, see, now to propose the mechanism for the reaction below 500 Kelvin, the experimental rate law will help us. See, experimental rate law suggests that the slowest step involves the concentration of NO2 only, and therefore in first step the NO2 will react to give. Now see, here one desired product is NO and another is CO2. So the probable product for the first step of this mechanism will be NO, which is desired one. And stoichiometry says that if NO will form, the another product that is formed will be NO3, which is not desired product for us. And therefore it is it can be regarded as intermediate product for the first step. As it is intermediate product, its lifetime will be very low. It will react very fast. Now it will react in next step with remaining reactant CO to give CO2 plus NO2, and therefore the overall reaction will be this. So from this example we can say that if we change the condition, the experimental condition of reaction, the mechanism of reaction will change. Above 500 Kelvin temperature, the reaction is single step reaction, depends on the concentration of both the reactants. But below 500 Kelvin, the same reaction is not elementary reaction, but it is complex reaction and depends on the concentration of one reactant, that is NO2 only. Now let us try to establish the relation between the experimental rate constant as well as the rate constant which is derived from the mechanism. For that we will take one example in which H2 react with Br2 to give 2HBr. Now the probable mechanism for the given reaction is in first step. See, this is the example which follows chain reaction mechanism, in which the first step the initiation will takes place, that is formation of free radical. This free radical will propagate the reaction, and at certain stage there will be termination of the reaction. So the probable mechanism for the given reaction is in first step Br2 will produce free radical Br, and this is equilibrium reaction, therefore naturally it will be fast. In second step, this Br will react with H2 to give HBr along with H, and in third step that H will react with Br2 to give HBr plus Br. From these three steps, this will be the slow step, this will be fast step. Now let the rate constant for this step is K1, for its reverse is K minus 1, for second step is K2, and for third step is K3. Now experiment suggests that this reaction follows one and half order of reaction. That means experimental rate law suggests that this reaction is first order with respect to H2 concentration and one half order with respect to Br2 concentration. This is the experimental rate law. Now our intent is to establish the relation between this experimental rate law, that is the experimental rate constant, as well as the rate constant which will derive from the mechanism. Now how one can derive the rate law from the given mechanism? That is the question. If we derive the rate law from the given mechanism, then and then we can establish the relation between experimental rate constant and the rate constant derived from the mechanism. Now to have the rate law from the mechanism, we should focus on the slowest step of the mechanism. By rule, the slowest step is rate determining step of reaction, and it will control the rate of overall reaction. Now in given mechanism, the second step is the slowest step, and therefore we can say from mechanism as step 2 is rate determining step, and therefore we can write R, rate of reaction, is equal to some constant. Now the constant will be K2 into the concentration of reactant, that is Br and H2. This is the rate law which is written from the mechanism. Say this is 1. Now compare this rate law which is derived from the mechanism with the experimental rate law, that is this. Now when we compare these two, it looks that here there is H2 concentration, here there is Br2 concentration, this is Br concentration. So we want Br2 concentration instead of this Br concentration. So we have to again modify this rate law by using the mechanism. Now for that we should consider the concentration which is desired for us and the concentration which which we do not want. Say here the desired concentration is Br2. This concentration we want and this concentration we do not want, and therefore we have to find a relation between these two in the mechanism. So looking to the mechanism, we can say that step 1 is the equation or the reaction which correlate Br2 with Br, but at the same time it is the equilibrium reaction, it is the fast reaction, and therefore we can write the equilibrium constant of reaction. So from step 1 we can write equilibrium constant of reaction, that is K equilibrium. Now we know that the equilibrium constant of any reaction is the ratio of the concentration of product to that of the reactant when reaction reaches to equilibrium, and therefore we can write K equilibrium is concentration of product, that is Br square by Br2. This will be cancelled. So K equilibrium is Br square by Br2. We want Br2 concentration in equation 1 and we don't want Br, and therefore we can write this equilibrium constant in terms of the concentration of Br, and therefore if we rearrange this equation in terms of Br, we can say Br square is K equilibrium into Br2, therefore K equilibrium into Br2, and therefore Br is concentration of Br is K equilibrium raised to half, that is square root of K equilibrium into square root of Br2, that is concentration of Br2 raised to half. Say this is 2. So equation 2 gives the concentration of Br. Now we can substitute the concentration of Br from equation 2 in equation 1. So from 1 and 2 we can say R is equal to K2 into Br. Br is this, that is K equilibrium raised to half into Br2 raised to half into H2. Now say this is equation 3. Now in equation 3 two constants are there. One is the rate constant for second step of mechanism and another is the equilibrium constant of first reaction. So this is the algebraic combination of two kinds of constant. Say it is one constant, that is K, therefore R is equal to constant K into Br2 raised to half into H2. Say this is 4, where this K is combination of two constant K2 into K equilibrium raised to half. Now again compare equation 4 with the experimental rate law. By comparing 1 and 4, we can say that h2 raised to 1 and br2 raised to 1/2. So this is the experimental rate law, this is the rate law derived from mechanism, and comparing these two rate law, as it involves the concentration of the reactants in same way, we can say that the proposed mechanism is consistent with the experimental rate law under this condition. If algebraic combination of different constants are like this, we can say that the proposed mechanism is consistent with the given rate law. So in this way, we can establish the relation between the rate constant derived from the mechanism and the rate constant which is observed in experimental rate law. Now let us try to establish the relation between the equilibrium constant of overall reaction and the rate constant of each elementary steps and their reverse reaction. And this relation is called principle of detail balancing. Or sometimes it is called